So I'm very glad to be able to tell you about some of the work that we've been doing in Australia and New Zealand. If you looked at the program, you'll see that the title's changed from what I had originally, but after listening to the talks today, I thought that the audience would probably be more interested in what I've got to say here. So this work has been done with a collaboration of a bunch of people. So I'm a theorist, but I like working with experiments, and there's two teams of experimentalists on here. But the real people who've done the work are Matt Reeves, who's a postdoc with me, and Oliver Stockdale, who's doing a PhD. So they've done a lot of the actual hard work. And the experimental teams, one of them is led by Tyler Neely. He does atomic gas bosons and condensates. Warwick Bowen does all sorts of things, but I'm going to be telling you about superfluid helium experiments that they've done. And this is the team of people that have all contributed to the work. So really, my talk sort of starts out by along the very similar lines to Tapio's similar. So I'm going to speed very quickly through the first part because he said a lot of the things that I really wanted to say. But the talk's going to be about 2D vortices and 2D turbulence. And I guess it all goes back to this paper by Onsager in '49 that came up with this, or was looking at this model of isolated point vortices in the context of 2D turbulence, and in particular the emergence of these large circular flows in two-dimensional fluid systems. And so his insight was to look at the 2D point vortex model, realize that it was a Hamiltonian system, and this meant that you can do statistical mechanics on it. And so therefore you can go ahead and do things like, calculate the equilibrium states of matter. And because of the funny way that the phase space works, it turns out that you get this regime of negative temperature. So the idea of you've got this Hamiltonian system, but like Tapio said, it's kind of a funny Hamiltonian system in that you only have two coordinates, or two spatial coordinates and no kinetic energy, and maybe you really should be thinking of that as a one-dimensional system. But this is a set of equations, and if you go ahead and calculate what the phase diagram looks like, this is the picture that was also in Tapio's talk, you get this sort of idea. So if you have a system of neutral sort of a negative vortices, then the lowest energy state is when you have all of those vortices paired up, and at a certain energy, as you go higher, they unpair and you go into this normal state where all the positions are essentially at random. But of course, there's a point of maximum entropy, and as you go to higher energies, you need to force like-sign vortices towards one another, and so the number of arrangements you can do for that goes down until you end up at the very end here where all the vortices like signs are arranged on top of one another. So it's all kind of interesting, but it's relevant to physical systems. It was even highlighted by Onsager. It's like, well, this is a nice model, but how does it really relate to the real world? And that's been a question for quite some time. But of course, when you come to superfluids, the vortices really are point-like objects, and a limit where you can sort of neglect their cause, and this actually becomes quite a quantitative model. And so, how does this relate to real physics? Well, I go back to again, the picture that Tapio showed. So he got interested in the system. If you take this circular superfluid with a flat bottom and you just imprint vortices at random and run a Gross-Pievsky simulation, what do you find? Well, you already saw the movie on Wednesday, but the end result is that you get a lot of vortex annihilation, but you get the ones that remain, the positive, negative ones, separate from one another, and then sort of all annihilations cease. And so you seem to be getting this emergence of these negative temperature states somehow through the Gross-Pievsky dynamics, whereas if you did the point vortex model of this, if you started out here, these things would just run around one another. There's no annihilation in the model, and so it would just sit there at that sort of infinite temperature equilibrium. Now, the explanation for what was going on, or the explanation we came up with, is that when you get vortex, anti-vortex annihilation, that's removing particles from the system, but of course the energy of interaction is quite small when they annihilate. They're quite close, so as you draw them apart, that's higher energy state. As they come together, it's lower energy state. But then when you delete them from the system, you're removing a relatively small amount of energy from the vortices, and so the energy per vortex of the remaining vortices goes up. And so the picture that we came up with is that we're starting sort of in this, we've engineered this infinite temperature state here, but this process of evaporative heating pushes this smaller and smaller systems of vortices to higher and higher energies per vortex, and you end up with this, these clusters emerging. Okay? Now, this is a risky strategy. Has anyone any questions at this point. That's awesome. Okay, so that sort of sets the scene. So now I'm going to tell you about some experiments and some modeling that we've done relating to vortices in 2D and the point vortex model. And the first slide is, in fact, this is like the summary slide of what Tapio already talked about. So essentially at Monash University, Chris Helmerson and his group, along with Tapio and helpers, they essentially did that experiment that we just showed you the simulation for. And so they stirred their system in such a way that they got these random arrangements of positive and negative vortices. They saw vortex annihilation. And although there's a relatively small number of vortices, they see this sort of evaporative heating process, at least hinted at in their data. And so they certainly saw transition from lower initial vortex energy with a sort of no real structure, but if they put in higher initial vortex energy, they end up with these sort of clusters at the end down here. Okay, so at the University of Queensland, we're also quite interested in this, and we're sort of attacking this problem. We're wondering about how we can do it. We were sort of developing different techniques along the same line. But what we wondered is, well, this is actually pretty interesting, but it's a pretty hard experiment to do, and I think what Chris has done is really quite fantastic. We thought we might try a easy attack, and we thought, well, can we actually create one of these negative temperature states by direct injection? So not having to rely on relaxation dynamics to give it to us, but just making it in the first instance. And so that's what we did. And so we're playing around with different ways of manipulating the condensate. So I guess I should just give a quick summary. So the experimental system is a rubidium-87 BEC. It's trapped in a laser sheet, so it's quasi two-dimensional. And then there's this digital micro mirror device, which is exactly the same sort of thing as you have projecting this picture on the screen. Basically, you can control an array of mirrors to turn the laser light on and off. And so you can project any sort of trapping potential you want in a time-dependent manner onto your BEC. And so here we've got a flat bottom trapped, and we've got these barriers that we introduce and drag through the system. And I could show you the movie, but it would take a little while. But what happens is you get these clusters of all these vortices coming off the edge of these barriers and forming these very tight clusters on either side of the system. Now, the reason that the trap is this elliptical shape has got to do with breaking the symmetry of the system. So if you had a circular disk and you want to make these clusters, they've got a tendency to wander around back and forth. But if you make it elongated, then the clusters tend to sit one side and on the other side. Now, the reason that we're doing this, I didn't say this, but part of the thing is that at that stage, we didn't have the ability to detect the sign of the vortices. And so I had to rely on looking at their positions. And the idea here was we'll go through with a procedure where we can reliably know that the vortices that we make, they're going to be, one side's going to be one side and the other side's going to be the other side. And so the experiments came out quite nicely. We did gross Podesky simulations with a small amount of dissipation added to sort of model what was going on. So what we found in an experiment is these clusters, they lived for a long time, but they slowly got larger and larger. And the idea is this has got to do with mutual friction with the thermal cloud that is always present. And so after about 10 seconds, they grow large enough that the vortices start merging into one another, and you can't really tell which side the vortex came from. And so we did another experiment, which is stirring, same sort of idea, but a different barrier potential. But the thing is that this injects vortices at a lower energy, so that, well, I don't want to go into too much detail, but you end up with the same number of vortices, but there is a lot of annihilation and they go away. And in principle, you could see the same sort of thing that Chris Helmerson did, but with sign detection, it's not possible. Now, it turns out we can actually do sign detection in the end, and we did sign detection on this and confirmed that vortices on the left and right were positive and negative. That reassured the referee that all was well. And so that's actually something that we could make use of in the future. But this was a real, I guess, a real limitation of what was going on. The sign detection, what can be done? So we've moved on a little bit from these results to think about what can you actually do with just a single sign of vortices. And so if you go ahead and just eliminate one sign, you just focus on injecting vortices of the same sign, it actually turns out basically all the same features of the neutral system are still there. And in some sense, it's even more interesting because even at positive temperatures, you have non-trivial vortex distributions. And so this, what we've got here is a plot of the entropy versus the energy per vortex along this axis. And it's got the same characteristic shape as what I was showing you before. So it's low entropy at low energies, high entropy in the middle, and low entropy again at high energies. The thing is, this is for a fixed angular momentum. So what that means is a fixed mean of r squared of all the vortices. And so in a circular trap, that quantity is preserved. And so this is looking for a fixed angular momentum. So fixed mean radius squared. And what you find, if you look at the density of the vortices in equilibrium, it changes as you go through the energies. So at zero temperature, all the vortices are sort of equally distributed. You'd get a vortex lattice. So this is sort of trying to picture what's going on there. It's not a lattice, as you can see, because my PowerPoint skills aren't that great. But as you increase the temperature, the vortices start moving around. And it turns out you go from having a square top distribution to having a Gaussian-like distribution. And that's at this maximum entry point here. But then you can keep doing the same thing. You increase the energy more, and your Gaussian gets squeezed. It gets, the vortices start attracting towards the middle. But then at a certain point, as they get closer and closer to the middle, all the vortices in the middle would correspond to 0 in terms of the mean radius squared. And so at a certain point, they've got to go off axis. And so there's this, something like a second order phase transition where this distribution goes off axis. And I have additional arrows. So the idea is that once you get to these low entropy states, this distribution gets narrower and narrower and narrower, shrinking down to a point, but off the axis. Okay? Yes? Yes. Experimentally? Yeah. Yeah, the images are in the Hamiltonian, yes. Yeah. It's all included. Okay? So that's gave us an idea for experiments. So can we use direct injection like we did before? So for example, can we create a bunch of vortices near the center and look at these sort of positive temperature states and look at their density? There are schemes where we can inject the vortices off axis, and so we get one of these broken symmetry states to begin with. But then the more interesting thing is, well, actually, if we can do this, what about if we create a state that is out of equilibrium? Can we watch its dynamics towards one of these point vortex equilibria? And so the idea is here, we're injecting a state with two clusters on either side of the condensate. So here, it's got a mean value of r squared, but if you look at the sort of center of mass of the vortices, it's at the center. But the Monte Carlo would tell you that actually, well, the most likely state is a single cluster with a slightly larger radius, but it's got a non-zero center of mass. Okay? And so that's what we did. And so I do have movies of how we create these different schemes, but the details are not important, but I'm very happy to show them to you afterwards if you like. But in this column here, we create a cluster of something like 15 to 20 vortices in the center. As we watch it evolve in time, this goes down to 6 seconds down here. So these are single realizations. You can see that you start off with a cluster of vortices. It's actually very hard to tell them apart at this stage, but at a certain point At a certain point, you can count them all. And along here, we've got a histogram of the vortex positions measured over an ensemble of experiments, something like 20 or 30, I think. And so you can see from this histogram that you get this sort of expanding cluster, which kind of fits with what we've got, what we've seen before. There's some sort of mutual friction that leads some amount of energy dissipation. This experiment here, instead of creating the cluster on axis, we create it off axis, and so you can sort of see it here, and there's a variety of different realizations, but basically the same sort of thing happens. It stays off axis, but the size of the cluster gets larger. So the most non-trivial system is where we create two clusters off axis, and it's a bit hard to see, but you can sort of see a cluster here and a cluster here, and at this time here there's a cluster here and a cluster here. But as you go to long times, it seems that the distinction between the two clusters goes away. And if you go ahead and take all the data and you rotate it such that the center of mass of the vortices is on the x-axis as much as possible, well, at the first instance, it's sort of spread everywhere, and so you can very clearly see that the mean dipole moment is 0. But then as time goes along, you can see it's sort of heading off axis. And so if you compare that with the Monte Carlo simulations, it actually seems that it fits pretty well. And so these are These are the experimental histograms from the previous slide, and these are sort of theoretical predictions of what it should look like based on Monte Carlo simulations. And down the bottom here, we've got a projection of the density along this direction. And so here, this is a direct comparison of the points are experimental data, and the curves are from those Monte Carlo simulations. And it seems that there's pretty good agreement there. But the most interesting thing is actually trying to model the dynamics of the system. And this is still a work in progress. It's not entirely clear exactly what's going on. But the first thing we thought to try is, yes, we just go ahead and use the standard point vortex model, and we'll put in a little bit of mutual friction to take account of that dissipation that you see, the sort of expansion of those vortex clusters. And so this is the point vortex equation of motion. So dr dt is equal to the superfluid velocity. So this is just a sum of the fluid flows of all the single vortices. And so each single vortex is moving in the flow of all the others. And this is the mutual friction term, which basically, if you had a single vortex, would cause it to slowly spiral outwards. Okay, and this alpha is called the mutual friction coefficient, I believe. However, when we made use of these equations, they didn't work. And it's not really, they didn't give, it was called a qualitative agreement with the experiment, but not quantitative. And so one of the things that we're wondering about is, how good is this model, and are there other things that are better? So one of the things we tried was, instead of having the dissipation, include sort of Brownian motion effect on vortices. So the idea is the vortices are getting kicked in random directions by the thermal cloud that's present. And it turns out that you actually get incredibly good agreement between the theory and experiment by doing so. So they're quite busy graphs, but maybe if you just focus on this one here. So we've got the three different cases where we inject vortices on axis, when we inject vortices off axis, and then second one, non-equilibrium, that's the two clusters diametrically opposed to one another. And so you can see here that you sort of start with a finite dipole. So let's start with the on-axis one. So you start with a dipole moment that is close to zero. It's not zero because when you have n objects and you're expecting them to be centered about the middle, there's always a square root of n non-zero amount, but this agrees with what that should be. And so you see that basically stays zero. If you put them off axis, you can see that there's a very slow decay of that dipole moment. Yeah. So that's a great question. Here it's a fitting parameter. It would be great to see if we can come up with a way of estimating what it is from fundamentals. Probably there is, but we haven't done it yet. Yes, so there's slow decay, but then of course the non-equilibrium case is the one that's interesting. So it starts with a dipole moment consistent with zero modulo finite number effects. But at a certain point in time, it jumps up to a finite value, and then it sort of slowly decays as well. Ricardo. That's another good question, and I think there is a factor of something like 50% difference between the two. So it's not exactly the same, but I think it's probably within the bounds of statistical uncertainty. So it's not just a dipole moment, but it's all the variables actually. So the angular momentum fits quite well. The number of vortices fits quite well. So actually the other thing is as you have these sort of additional parameters of point vortex Hamiltonian, vortices like wander around and they go out the side of the disk. And so we have to add an annihilation of those vortices by hand. So they would annihilate with their image. And so here you can see the number of vortices actually goes down from 15 to something like 11. But even when you go ahead and calculate the energy agrees as well. You might wonder why there's no fitting parameter for this part of the red system, but this is the region where you can't resolve the number of vortices, so you can't entirely be sure of how many are present because they're overlapping with one another. So that's a great question. So both the theory and the experimental data is after an ensemble averaging. Anyway, so we thought that was pretty neat, but we still have some of these open questions that we're just trying to finish off before we write it up and submit it somewhere. So that is essentially the end of the first part of my talk, and I'm glad to see that I'm basically exactly on where I wanted to be. So what have we done? We've done these experiments that actually quantitatively connect to this point vortex model that was originally thought to be a toy model, but turns out that it actually can be quite quantitative for atomic gas BECs. I didn't mention, so these systems are, well, I think I did mention actually, so these systems are quasi-two-dimensional. And so while the systems are actually three-dimensional in nature, the vortices behave like two-dimensional objects because it takes a lot of energy to excite a Kelvin mode. And so what we've shown is along with injecting these equilibrium states, we can also inject non-equilibrium and follow their relaxation to negative temperature. We did that by using systems of the same sign vortices, so we didn't have this issue of vortex annihilation. Yeah. Yes, both phenomenological. Yes. Yeah, so qualitatively they both give the same answers, but the quantitative agreement needs the Brownian motion. And I think in reality you should have a combination of both the dissipation and the noise. So fluctuation dissipation theorem applies here, I would think, but we haven't gone through the details. So in a model where you add dissipation, you should also have randomness as well. So sorry, I didn't hear. Yes, that's right. So probably, you know, we should combine the two of them together, and the coefficients of the noise and the dissipation should be related to the temperature. Yeah. So we haven't done that, or we have done that, but we haven't done it correctly, perhaps. Yeah. Hopefully. So I must admit, I can't remember the details. So I'm pretty sure Matt Reeves has tried this, but there was some issue with it, so I can't remember the details. I'm sorry. So what I'd like to hear from this audience, if not now then later, is what can we do with this system? So it's a really nice experimental system, and it can even sort of, you know, you can do a lot of stuff really controllably. So for example, down here I've got showing a method. It's idea was really due to Brian Anderson. But basically, if you take a potential and you drag that potential forward and split it into two, you can create a anti-vortex pair, and the vortices get trapped on those potentials. And then, so that's what's happened here. And then when you remove those potentials, if you can see, there's a vortex here and a vortex here. And so you aren't limited to doing only two. So over here, there's an example where we've created 4 vortices, and so having 2 potentials and splitting up like this. And there's even an example where we've done 8. And so there's a capability to make arrangements of vortices and move them around and put them where you want, and to let the dynamics go. And so, you know, I guess what are the interesting experiments we could do by controllably arranging vortices in 2 dimensions? Okay, so with the second part of my talk, I'd like to tell you about some experiments with 2-dimensional superfluid helium. So I'm really a quantum gas guy. Yes. Yes. Yeah. So if we go back to this one here, so these 2 clusters were separated from one another for about 10 seconds. Okay, so in the meantime, atoms are being lost, things like that. But after 10 seconds, it got to the stage where you can't be sure that one vortex that you see was from the left or from the right. And so, but that's purely limited by the fact that we can't image the signs, and so probably it lasts even longer. And I think the limitation is purely finite temperature. So if you're able to make it colder, I think it would last for longer. And like I said, so this experiment now does have that sign detection capability as well. So would be, you know, that's an additional bit of the mix. Okay. So I'm, like I said, I'm really a quantum gas guy. I'm not a superfluid helium guy, and so I'm a bit worried that some people are going to ask me questions that I'm not going to be able to answer here. But I'd love to learn, and so I'm very happy for you to school me at the end of my talk. So this is experiments done in the group of Warwick Bone. They got some really interesting results, and we started talking to them, and we helped them out with the modeling of their system, but there's still a lot of questions to be answered. So really the sort of physics that the Bowen group's interested in is cavity optomechanics, and so I thought, given the audience, it's probably worth just spending a couple of minutes explaining exactly what that means. And so this is my picture of what's going on. Cavity optomechanics is when you have an optical cavity, but for example, the back mirror is attached to a spring. And so the idea is if this was a totally rigid spring, then the cavity would have a very well-known sort of dispersion relation. But the trick is once it's got some sort of a spring constant, then the amount of light in the cavity affects, applies pressure to the mirror and it applies a force to that spring. And so there's a relatively complicated interaction between the light that's in the cavity and the mechanical motion of this mirror. And so the idea is that if you sort of start with a certain amount of light in the cavity, as this mirror moves back and forth, it changes the resonance condition of the cavity, and so the sort of steady state of light, or the intensity of the light that sits in that cavity goes up and down as the mirror moves back and forth. And so that's the idea of the system. If you sort of monitor the light that leaks out of this cavity, as the light goes up, that tells you that the mirror is moving one way and moving back the other way. And so if you take this signal here and you look at its power spectral density, that can tell you about the motion of that mechanical object. Okay? So this is just a schematic. So the system that the Bowen group was interested in is actually what they call a microtorr. So this is made of silica fabricated using lithography techniques. And the idea is that this sort of rim around the edge is a whispering gallery mode cavity. And so if you bring an optical fiber and taper it down to very close to this, you can cause light from the fiber to be coupled into that cavity, and then it behaves exactly like the system I had before. But instead of the mirror on a spring, what's going on here is that you can use the light to control the mechanical motion of that toroid. And so you can both detect and control the vibrations of that toroid. Now, of course, at room temperature, there's a lot of thermal motion of all these mechanics. And so that complicates the experiments on this sort of thing. And so to get rid of some of that noise, of course, what you want to do is cool it down. And so what they thought they'd do is they'd cool it down with some liquid helium. And so they pump their chamber full of helium gas, and I don't know exactly how it works, but they pump it down and they cause the temperature to go down. And they go from the point where they're in the helium phase diagram where they're at the vapor, and they end up creating a superfluid without going through the liquid phase, all on the walls of their system. And so the original motivation was just to, let's make it cold and do mechanics of this microstructure. But what they found is if you look at the optical, or the transmission of their resonator, what they found is as they went through the superfluid transition, they got all these funny features that appeared on the blue detune side of the spectrum. And they found that these are not related to the mechanical motion of the microstructure because the power that was interacting was too small, basically, to have any effect on the mechanical modes of the microtoroid. And so the idea was, or what it appeared to be, is that somehow this light was interacting with the superfluid. And if you do the same sort of measurements as what we did previously, so measure the transmission, or the light leaking out of the cavity as a function of time, take the Fourier spectrum, what you find is that above the critical temperature for superfluidity, so this is modified from bulk because it's in a vacuum, so it's something like 1 Kelvin, I think, rather than 2.17. So there's nothing interesting in this spectrum above the critical temperature. But below the critical temperature, all these spikes turn up. And the evidence seems to suggest that this has to do with third sound modes of superfluid helium. And so basically the light that's leaking out of the cavity interacts with the superfluid, and if you shake it in the right manner, it can cause excitations of the third sound, or it can just monitor the thermal occupation of those third sound modes. Okay, so if we focus on one of them in particular, what you find is as you cool down the system, so 0.53 Kelvin is the lowest temperature they could go to in this particular realm of experiments, what you find is that the peak goes from being very broad and relatively undefined. As you get colder and colder, it gets sharper and sharper, and you can sort of track this peak as a function of temperature. It changes in frequency. The reason is because the thickness of the superfluid helium film is changing. As you go colder and colder, it gets thicker and thicker. And so they've done this work published in Nature Physics in 2016, sort of modeled all this interaction and found pretty good agreement between their modelling and the experiments that they made. Okay, and so what they did things where they used the light to, to increase the occupation of a particular mode and laser cool a particular mode and things like that. Okay, yes? Sorry, yes. Yeah, so this is one of the things I'm not very clear on, but third sound has to do with the change in height of the superfluid. Okay, and this is the type of excitation that you get in thin helium films. But beyond that, I must admit, I'd kind of think of them as Bogoliubov modes, but I know that's bad, but that's the picture I have in my head. Okay. And so what are the modes? Well, if you go back to that experimental apparatus, it looks pretty complicated. But the idea is that, this isn't quite accurate, but the modeling is done by treating the coupling to the system as a disk of superfluid. And so this is a very sharp boundary, and the thought is, I don't know how accurate it is or otherwise, but there's no mass flow. Well, they treat it as there being no mass flow over this point here in the film. And so I don't know how accurate or otherwise it is, but that's the sort of the assumption going forward. But if you make that assumption, then they can sort of do calculations and come up with frequencies that agree with the measurements from the quantum optics. Yes. So it's not the disk moving, it's the superfluid moving, and it's density oscillations in the superfluid. So this is a picture of what's going on. So this is plotting the change in density as a function of position. And so you can go ahead and model, if you assume that it's a circular disk, then you can go ahead and show that the excitation modes look like Bessel functions, and so they've got these mode numbers, and you go ahead and identify the shapes of the oscillations. Okay? And so this was all work that was done in 2016. Now, what I'm going to tell you about is more recent experiments where they sort of, rather than just sort of cooling down and measuring the modes, they try and do something to the system. And so what they did is they start off by cooling down to their particular temperature, but then they pump in a lot of laser light. Okay, more than just an amount to probe what's going on, but it's something that the superfluid absorbs light, it gets hot, and the thought is that there's evaporation of helium from that surface. And so, of course, what that means, oops. Okay, all right, I'm missing I thought I had another slide there. But what it means is, or what you might think happens, is superfluid rushes up to accumulate back on the surface to come back towards equilibrium. Doing this experiment, if you go ahead and do the same sort of thing to probe those third sound modes, what they find is, whereas previously you had this gray curve, after doing this procedure, what they found is that this peak had split into two new peaks. And so the question is, what's going on? And not only that, but if you look at one of them in particular, you find out there's a splitting, but as you wait for time, you find that it gets smaller and smaller and smaller as time goes by. And it's not just one particular mode, they can actually go ahead, so this is a spectrum across a wide range of frequencies, but they can go ahead and they can identify a lot of areas where previously there was one peak and now there are two peaks. And so it seems that there's some sort of splitting happening to a bunch of these third sound modes. And so the idea of what's going on, this is sort of a representation of one of these oscillations. And of course, if you've got something doing this, you can actually think of that as being a clockwise and counterclockwise circulating excitation. And in a situation where there's no fluid flow, then those two things have the same energy, or the same frequency. Now, imagine what happens, so a single frequency. Now imagine what happens if you put a vortex in the middle. Well, experiments like this have been done in boson-Einstein condensates. These guys down here have done experiments like this in thin helium films as well. And so this was done, this was done back in the 80s with macroscopic systems, but they sort of created a system where they injected vortices and they saw the splitting of the frequencies of the two counterpropagating modes. And so the idea is that maybe this is what's going on in this experiment, that this heating of the system, it puts it strongly out of equilibrium. As it equilibrates, there's some creation of vorticity, and then that sort of slowly relaxes back with the decay of vorticity of time. Now, if you go ahead and model what's going on, so basically you go ahead and put a superflow on the background of these vortices, well, imagine a single vortex to start with. So you can look at the frequency splitting that happens with each of these different modes if you imagine you have a vortex in the middle of the system. And actually you can go ahead and take that vortex and move it from the middle of the system out to the edge of the disk. And what you find is in the center, that's when you get the largest frequency splitting, but then as you take it towards the out, it goes down. But each of the different modes, the behavior of that splitting as a function of velocity is different. Now, why is this important? Well, if you go ahead and you measure the splitting of a lot of different modes as a function of time, they've actually chosen 5 different modes, and you can see how the splitting evolves. But the idea is that maybe by combining all this data, you can work out if there are vortices in the system, how many vortices are there at what radius as a function of time. And so this is a way of detecting the presence of vortices on that disk and their subsequent dynamics. Yeah. Is it unique as in can you identify the X and Y position of all the vortices? No, it's not. So there's only 5 pieces of data, and of course if there's multiple, many vortices, then you certainly can't do that. But you can do better than nothing, so I'm going to tell you. Okay? Yes, so I guess, well, the thought is if you could detect enough modes, and in principle maybe you could triangulate every single vortex, but I don't think, well, it's certainly not possible at this point in time. Okay, so it does seem that there's some sort of circulation in the system. It appears that it's decaying, but the question is what the hell's going on? We've only got these 5 pieces of data as a function of time. And so that's where I came in with Matt and Oliver. And so we thought, well, can we come up with a picture of what's going on in terms of the point vortex model? And so the experimentalists had some ideas, and we went through a bunch of these ideas. But what we're going to do is use a point vortex model with this mutual friction that causes some dissipation. And so there's 4 sort of different scenarios that we tested. First one was maybe there's some sort of cluster of vortices initially, and that slowly expands, and as those vortices move out, that results in those splittings going down. Next one is they had some idea that there was a cluster in the middle, but there was pinning. Maybe there's pinning on the site. And so we put in different models of where pinning might be, and point vortex model with additional pinning added in. Now, if you remember back to the initial picture of the system, there was this pedestal that came up to the system. And so maybe this was some form of trapping potential for circulation. And so there's another idea, well, maybe there's some sort of circulation trapped on this pinning potential, and that every now and then vortices escape and translate, or move out towards the edge, and so the total circulation goes down as a function of time. The fourth one that we looked at is maybe there's some sort of pinning of vortices in the center, but then there's vortices of another sign circulating around the system, but then the mutual friction causes them to spiral in and slowly annihilate the vortices that are sitting in the middle, circulation that's sitting in the middle. Now, I don't want to go through all the details of how that worked out, but it turns out that this model here is the one that gave the best agreement with what was going on in the experiment. And so without going through all the details, basically what we did is we made the assumption that there's some number of vortices in the middle, equal number of vortices circulating somewhere around the outside, and we went ahead and did a lot of Carlo simulations of the system at equilibrium. So as a function of energy, of angular momentum, and the number of particles present. And went ahead and calculated what all those splitings should be as a function of all those different equilibrium states. And what we found is that actually you could constrain quite well, making that assumption, you could constrain quite well what was going on in an experiment. And so you can go ahead and calculate the energy, or the kinetic energy of the flow, and of the cluster of vortices that was going around outside. And so, for example, in this scenario here, this is what these vortex distributions look like on average as a function of time. So again, this is sort of ensemble average over many realizations. And it turns out if you go dive into the data, it actually constrains the vortex number quite well. And so based on this fitting, you can sort of say, well, this is the number of vortices you have as a function of time throughout the experiment. So this is the number of vortices that are pinned in the center. So these are just pictures of the vortices that are not pinned in the center. Okay. So that's just sort of taking equilibrium data and fitting to the experiment. Yeah. Yep. Yes. So that's actually quite an interesting question. So it turns out that all the so this is without modeling any dissipation actually at this point. It's just saying this is a set of states that we have based on number of vortices, energy, angular momentum, what fits best, what fits the experiment best. And it turns out that these are the numbers that fit best with relatively small uncertainty. I mean, these could be all over the place if it wasn't a good fit. It turns out that a lot of the states, they just don't predict the splittings, or the splittings that you'd get don't agree with what was measured in the experiment. So the line is an experiment, and the shaded region is the range of uncertainty based on what fits the data best. And so you can see here there's sort of some uncertainties in these vortex numbers, but this is sort of the best fit vortex number. Yes? So that's a really great question. So the question is, which side of the disk is this happening on? Do you have vortices on both sides of the disk? So as experimental understanding progressed, it seems that the vortices are all on the underside of the disk, and so this is where the pedestal is. And so the experimentalists tell me that they can actually detect the difference between the top and the bottom because the modes on the top and the bottom have slightly different frequencies, and the ones on top, they don't see the splitting, but the ones on the bottom is where they see the splitting. But this is all assuming that you can treat these as two independent disks of superfluid. I'm not sure how good an approximation that is. I would have thought superfluid is everywhere. So how does that work out? I still don't understand that. Tapio. Yeah. That's a good question, and the answer is no, it's not. But we don't think it makes a big difference. But we're not 100%. I'm not 100% sure of that one. Yes. Yeah, so look, that's a real question for me, and how you resolve whether that's a reasonable thing or not. I mean, the idea is maybe you can do a gross pedestrian model of the whole three-dimensional system, but that's a pretty hard calculation. But you can come up with a mock version of doing that, where I think it would be quite feasible, and I would like to do that sometime soon. Okay, so back to the question about mutual friction. This is all just fitting sort of equilibrium states. Now, you can also go ahead and actually do dynamics. And where was my slide with the model? Oh, okay, no, it was back here, wasn't it? Okay, so we also have gone ahead and done modeling using point vortex model with this mutual friction. And what we find is that actually you get very good agreement in the shapes of the curves between the experiment and theory. And so this is a result where, this time the blue line is the results of a single simulation, and the shaded region is a result of an ensemble of simulations where we've taken different microstates with the same sort of energy and angular momentum and so on. Now, with regard to the size of the mutual friction, now these experiments last for like 6 minutes. And so the actual value of the mutual friction is tiny, tiny, tiny. And so these vortices are going around, 1 million times before there's any appreciable dissipation. And so what we did is we actually did simulations with a much larger value of the mutual friction. And so the simulations happen on a more reasonable timescale. But what we looked at is what happens if you change that mutual friction as, you double it, or halve it again, halve it again. And what we find is that the time axis is really, beyond a certain value, it scales. And so if you make your dissipation 10 times smaller, all that means that you scale your time axis by a factor of 10. And so the simulations were done on a relatively large mutual friction. We stretched out the axis to the value of time that matched the experiment and modified our estimate of the mutual friction coefficient. And it turns out that it actually agrees quite nicely with other papers on this sort of system, where it's been measured before. But I must say I'm not up on the details of that. Okay, so it looks like I've come to 45 minutes, and so that's the end of my talk. So this has been written up and it's been submitted. We've got some excellent feedback from referees, which has helped improve things. There's still many improvements that can be done. So the claim is that this, somehow this is a real-time detection of the dynamics of vortices in the system. And out of the comparison with the simulations, you get a measurement of the coefficient of mutual friction. One of the referees asked, can you measure this as a function of temperature? And it's like, well, actually that's quite an interesting comment. And in principle, yes, you can do this experiment at different temperatures. This was done on an older version of the apparatus. It was limited to how cold it could get, but the new version of the apparatus is much more capable. So there are plenty of unanswered questions. The new version experiment, like I said, this previous one was aimed at doing the mechanical modes of that oscillator. I've now created these systems where it's aimed at doing superfluid experiments, and so they don't have the same shape of oscillator. It should be easy to understand. So you could, for example, measure the mutual friction. They have the goal of trying to track the dynamics of a single vortex. How realistic or not that is, I'm not entirely certain. And this, I didn't mention, but this is all done with films about 8 nanometers depth. And so it was, again, the same situation where it was only quasi-2D. The superfluid's definitely 3D. The healing length is something like half an angstrom, half a nanometer, I think. Sorry. But there's no reason, in principle, why you couldn't go to thinner films and to do experiments on BKT physics. And again, as there are interesting experiments we do here on 2D quantum turbulence. So with that, I'd like to thank you for your attention. Yeah. I think what they tell me